Let's take what we know about building a model, look at a new example, and use that model to predict what's going to happen in the future. Again, we're going to take data. We're going to use that data to build a model. And then we're going to use that model to make predictions. Every single time we're doing a problem, that's essentially what we're going to do. We're going to take the data, build a model, and then use that model to make predictions. So, let's look at the data. Notice I'm completely ignoring the questions because the question has nothing to do with building the model. Let's just look at the given information. I have 15 cute little bunny wabbits that escaped from a cosmetic testing facility. After 4 days, there are 27 cute little bunny wabbits. So notice I have an initial condition of 15 cute little bunny wabbits, and then I have a secondary condition of 4 days gives me 27 cute little bunny wabbits. I have an initial condition that's going to help me find the C value, and I have a secondary condition that's going to help me find the K value. So let's do it. Starting with y equals CE to the KT, I know the initial condition is 15, so at time 0 we have 15. We can just replace the C with 15. The secondary data I had, the secondary condition, was after 4 days there's 27 bunny wabbits. So y of 4 equals 27. So I can plug in 27 for y and 4 for t to help me figure out k. Cleaning up that exponent, just writing 4k. And then, just as we did before, we can solve for k. Go ahead and pause here. Hit play when you're ready when you have solved for k. Alright, so we're going to divide by 15. Take the ln of both sides. E and the ln are going to cancel out immediately. We're left with 4k on the right side. Divide by 4, and we have our k value. At this point, I always like to look at that k value, think about the reasonableness of this answer. Now notice ln of 27 over 15. 27 is larger than 15, so this is ln of a number that's greater than 1, which means this is a positive value. Because we started at 15 and we're ending at 27, we know we're growing, so it makes sense that k would have been a positive value. So I'll take that k, plug it back into my law of exponential growth and decay, and I can either leave this as my model and use this to make my predictions, or I can use the simpler version of the model where I cancel out the e and the ln and bring the 27 over 15 downstairs. So that would be the prettier of the two models. Again, I don't care which version you use, but I am never going to use this one. I am always going to use this one. So now that we've built our model, let's go back to what the original question had asked. So the first part of the question said, how many bunny wabbits will there be after 2 weeks? Notice the question is asking for how many. We have a y and we have a t. I'm asking you for how many, which means we're looking for the y value. The t value is the time, 2 weeks, but be super careful there. Notice the unit that time is being measured in. When we built the model, we built it on a time unit of days, which means once we've established the units, we have to continue with those units all the way through. 2 weeks is not actually 2 weeks. We have to make sure that we use the same units, so 2 weeks is actually 14 days. Make sure you're always using the same unit all the way through the problem. Once you've established the unit when you build the model, you have to continue using that particular unit. So what we have is how many bunny wabbits will there be after 14 days, or y of 14 equals what number? Well, easy. Let's just take 14 and plug it into the model. Plugging in 14 into the model gives me this. Now technically this would represent my exact answer, but I assume you have a calculator handy, so go ahead and pause here, type this expression into your calculator, and let me know what you get. Alright, if you plug that in correctly, you should get about 117. Now, of course, in general, we say to always give me 3 digits past the decimal, but we're talking about physical rabbits here. So when we're talking about a population, it's customary to just round it off to the whole number. So about 117 bunny wabbits after 14 days. Now let's look at part B. How long does it take to get to 500 wabbits? Question, how long? We're looking for how long. So what are we looking for? We're looking for a time. We're looking for t. The 500 would represent the y value. y representing the population, t representing the time. So we're looking for the time when y equals 500. So this time we're going to plug in 500 for y, and we're going to solve for t. Notice the variable is in the exponent, so we're going to use techniques for solving exponential equations. Pause here, play when you're ready. All right, one of the most common mistakes I often see is people will try to cancel that 15 right there. Keep in mind, this 15 is part of the base of the exponential, which is being raised to an exponent. Just like I can't multiply 15 times this, whatever this number says, because of the exponent, I can't cancel out the 15s. The 15 is trapped inside of the exponential expression. Just follow the rules of solving by isolation. The goal is to get t by itself. The outermost operation is 15. That 15 is being multiplied by the exponential, so let's divide both sides by 15. When I divide by 15, I get 500 over 15 on the left side. Now, of course, both of those numbers are divisible by 5. I could simplify, but as I've said many a time before, I don't care what happens on the non-variable side of an equation. If you want to simplify this, you go right ahead and simplify this. I'm going to leave it alone. I'm going to let the calculator do the work at the end of the problem. I'm just going to leave it as 500 over 15. The goal is to get t by itself. T is part of an exponential. I need to get rid of the base. The way I'm going to get rid of an exponential is using a logarithm, so I'll take the ln of both sides. This time, though, the ln doesn't cancel anything out because it's not ln of e. I'm just going to keep going by bringing the t over 4 to the front as the coefficient, using my log properties. The goal is to get t by itself. T is being divided by 4, and it's being multiplied by ln of 27 over 15. Multiplication and division are the same operation, so I can get rid of both of those at the same time. I'm going to multiply by 4, and I'm going to divide by ln of 27 over 15. So here's me taking the left side and multiplying it by 4 and dividing by ln of 27 over 15. Notice t is by itself, which means I'm done. That is my exact answer. But of course, that answer doesn't mean much to me without approximating it using a calculator. So take a moment, grab your calculator, type that in. Let's see what you get. Pause here, play when you're ready. If you type it in correctly, you should get about 23.863 days. Now notice, this time I did not round off to the whole number. I gave 3 digits past the decimal. If we're talking about rabbits, if we're talking about a population of rabbits, then it would be appropriate to round it off to the whole number. Y represents the population. What we just did is we solved for t. T represents time. You can subdivide time. It's much less bloody than subdividing rabbits. So time is perfectly fine to give 3 past the decimal. So 23.863 days, so a little bit less than 24 days. Final answer. Let's take a look at another example. Another population problem. A small town has a population as given in the chart below. In 1985, the population was 2,500. In 2010, the population was 3,350. I want to predict the size of the population in 2020, and assuming continued exponential growth, when will the population be double its 1985 population? So let's start by ignoring the question completely and focus on the given information. We're going to use that given data to build our model, and then we'll use our model to make our predictions. Now, first off, I need to know where I'm starting. Well, keep in mind, time did not start in 1985, but for the purposes of this problem, we're going to treat it as if that's time 0. So for the purposes of this problem, time begins in 1985. That's time 0, which makes 2010 t equals 25. Anytime you're given a calendar year, don't actually use that calendar year as your time. Convert it to a starting time to be 0 and then time after that starting time. 1985 is t equals 0, so 2010 is 25 years later, so t equals 25. Now, since at time 0 the population was 2,500, we're going to call that the c value, and we'll use 3,350 as our secondary value. So y equals c e to the kt is actually y equals 2,500 e to the kt, and we'll use that secondary value, 3,350 at time 25, to solve for k. Go ahead and pause here and solve for k. Hit play when you're ready. All right, so just like before, we're going to divide by 2,500 as our first step. Now, again, I always say don't bother with simplifying on the left side, but in this case, it's we have trailing zeros on both the numerator and the denominator, so I'm going to go ahead and cancel out the 0 so I don't have to write them every time. And again, if you want to simplify the 335 over 250 further, you go right ahead. I'm just going to leave it alone. So I have e to the 25k on the right. I need to solve the exponential, so I'll take the ln of both sides. That's going to cancel out the e on the right side, leaving me ln of 335 over 250 on the left, and then divide both sides by 25. Taking that k value and plugging it back in to get my model, and then canceling the e and the ln, bringing the 335 over 250 downstairs to get my simpler version of the model. I now have a usable version of the model. Now let's actually start the problem. Predict the size of the population in 2020. Now recall, 1985 was t equals 0, which means 2020 is actually t equals 35. Don't go plugging in 2020 in for t, that wouldn't make any sense. So we're going to plug in 35 for t to figure out what the y value is. So plug in 35, type this into your calculator, let's see what you get. Again, make sure you're actually typing this into a calculator and not just continuing to watch the video. You need to make sure that you actually know how to use your calculator. I'm not going to show you how to use your calculator on the test day. So if you typed it in correctly, you should be getting 3,766-ish. Remember, this is the y value representing the population, so we're just going to round it to the whole number. Assuming continued exponential growth, when will the population be double its 1985 population? Well, if in 1985 the population was 2,500, what I'm asking you is when will the population be 5,000? So we want to solve for t when y equals 5,000. So let's plug in 5,000 for y and solve for t. Pause here, play when you're ready. All right, so we're going to follow the exact same steps in the exact same order, and as we go through each of these examples, you're going to see it's pretty much the same thing every time. So step 1, divide by that c value of 2,500. Now this time I went ahead and actually performed the division on the left side because it said that we're doubling. 5,000 is double 2,500, so it would be simpler just to keep writing 2 instead of writing 5,000 over 2,500. So I'm going to simplify when it's super simple and super obvious. I'm not going to simplify when it's not super simple and super obvious. Take the ln of both sides. That allows me to bring the t over 25 to the front. To get t by itself, I'm going to multiply by 25, I'm going to divide by ln of 335 over 250, and I get my t by itself, so that is my exact answer. And typing that into a calculator, I get about 59.209 years. But that's not my answer. The question said, when will the population be double its 1985 population? It did not say after how many years. It takes 59 years to get there. But that doesn't answer when. Because the question asked, when will the population be double its 1985 population, and I got 59 years, let's add 59 years to 1985, and we're going to get the year 2044. Final answer. All right, here's another example. Now we just did 2 examples. Hopefully you've got the hang of this now. So go ahead and pause here, try this example on your own, and then hit play when you're ready. Okay, 25 zombies attack a small town. After 6 hours, there are 50 zombies. How long will it take to have 500 zombies? Now notice, there are 3 sentences here. The first sentence represents your initial condition. The second sentence is your secondary condition, 6 hours, there are 50 zombies. And then the third sentence is the actual question. How long will it take to reach 500? All right, so let's break this down one piece at a time. Starting with the initial condition of 25, we can plug in 25 for C. And then the secondary condition, 6 hours produces 50 zombies, so 50 would be Y and 6 would be T. Solving for K, we're going to get ln of 2 over 6. And we'll take that K value, plug it back in to create our ugly version of the model, and then cancel the e and the ln, bring the 2 downstairs to get the simpler version of the model. I'm going to use that simpler version of the model to answer the question, how long will it take to have 500 zombies? I plugged in 500 for y, and t is what we're solving for. I'll then do basically repeat the process that I used for solving for k, because it's an exponential equation. I'm going to solve for t, divide by 25, take the ln of both sides, bring the exponent to the front, t over 6 times ln of 2, multiply by 6, and divide by ln of 2. So that's going to be the exact answer, and my approximation would be about 25.931 hours. This time it asked how long will it take, so 25.931 hours answers the question that was asked. Here's a very similar example to number 3, but this time I had a little bit more fun with giving you the initial data. So take a moment, read the question carefully, see if you can figure out what all the initial data is before I spoil it for you. Pause here, play when you're ready. So on January 1st, 1525, a small Italian village had a population of 2,500 people. During their super awesome New Year's party, someone starts coughing and boom, plague. By Pi Day, the village had a population of 2,000. At this rate, what will the population be by perfect square day? Now, hopefully you got at least the initial condition there. January 1st, 1525, we're going to define that to be t equals 0, and then the appropriate c value at t equals 0 will be the 2,500 people. All right, so at time 0, we've got 2,500. Now, the secondary condition has to do with Pi Day. Now, of course, you, the astute mathematician who takes any opportunity to celebrate, know that Pi Day is on March 14th. Now, if January 1st is t equals 0, what's the t value of March 14th? Hopefully you know how a calendar works. There are 31 days in January, there are 28 days in February, and since it's March 14th, we want the 14th day of March. Now, of course, you might be saying, well, some years February has 28 days, some years February has 29 days. Well, it only has 29 days on leap years, and leap years are years that are divisible by 4, and 1525 is not a leap year. So 31 plus 28 plus 14, that's going to give me day 73 of the year. If January 1st is day 0, then March 14th or Pi Day will be day 73. And keep in mind, on day 73, the population was 2,000. At this rate, what will the population be by perfect square day? Now, I know you know what perfect square day is. Perfect square day only happens every few years because it's got to be a day that, if you take the numerical value of the month and multiply it by the numerical value of the day, you get the year. So in 1525, perfect square day would be May the 5th, 5/5/25. I'm sure you knew that. Just like we did to figure out Pi Day, May the 5th, that's going to be 31 days in January, 28 days in February, March has 31 days, April has 30 days, and then we want the 5th day of May, so that would be day 125. So now that we have the appropriate data, take a moment and build the model. Pause here, play when you're ready. Okay, so y equals c e to the kt, c is 2,500. Use the secondary condition, the 73 and the 2,000, to plug in to solve for k. Divide by 2,500, take the ln, and then divide by 73. I'm going to get ln of 4/5 over 73. In this case, I simplified the 2,000 over 2,500 to 4/5 because this would be an example where I just thought it was super simple to simplify it, so I went ahead and did. Taking the k value and plugging it back in, I'm going to get y equals 2,500 4/5 raised to the t over 73. The question was asking what will the population be by perfect square day, which is day 125 of the year. Plugging in 125 for t, I get this expression. Take a moment, type that into your calculator. You should get about 1,706. So we started with 2,500 people. By day 73, there was 2,000 people. By day 125, there are 1,700 people.